So here are some numericals based on the ray optics. So the first question is, a candle of length 4.5 centimeter is placed at 12 centimeter away from a convex mirror of focal length 15 centimeter. So give the location of the image. It means you have to find the image distance. To understand the question clearly, better you draw the given question. There is no marks allotted for drawing the diagram, but for your understanding you can draw the image of a given question. So what they have given there is a convex mirror. So there is a convex mirror, a candle of length 4.5 centimeters. So H is of 4.5 centimeter, which is placed 12 centimeter away from the mirror. So it is 12 centimeter away from the mirror. So object distance U is 12 centimeter. This is U. Of focal length 15 centimeter. So as it is diverging the incident light, its focal length is here. So you can write the focal length inside the mirror. So here is the F value 15 centimeter. So looking at the diagram, give the sign convention. So the light from the object falls on the mirror. So this is the direction of the incident ray. H 4.5, as it is above the principal axis, it is positive. H is equal to plus 4.5. U, object distance. Object is placed at a distance of 12 centimeter. This is the direction of the incident light towards the right. According to the sign convention, distances are measured always from pole of the mirror. So pole of the mirror to the object. The direction of measurement is towards the left. So as both are opposite, the object distance is taken negative, minus 12. Focal length 15 centimeter. From the pole to the principal focus, direction of measurement is towards the right. It is in the direction that of the incident ray, towards the right. Then F is taken as positive. F is taken as positive. Now to solve this, we are using which all are quantities given. U and F are given. So V is asked to calculate, which is the formula that contains U, V and F. The mirror equation. What is the mirror equation? 1 upon F is equal to 1 upon U plus 1 by V. What required is the V value. So rearrange the equation. It is 1 by V is equal to 1 upon F minus 1 upon U. So 1 upon V is equal to 1 upon 15 plus 1 by 12. So 1 by V is equal to 9 by 60, or V is equal to 60 divided by 9. So this implies V is equal to 6.7 centimeter. So image distance is 6.7 centimeter from the pole of the mirror. So this is a simple example. We'll move on to the next question. So an object of 3 centimeter. So H value, height of the object is 3 centimeter, is placed 14 centimeter in front of a concave lens of focal length 21 centimeter. Find the position, nature and size of the image. So what all is asked? Position means V value, image distance is asked. Size of the image means H dash is asked. And nature means whether the image is real, inverted, or magnified or diminished. Whatever is the nature, you have to describe at the end. So for our understanding, we'll draw the diagram of the given question. So what they have given, a concave lens they have given. Concave lens, 14 object is placed at a distance of 14 centimeter. Object height is 3 centimeter. Okay, so light from the object falls on the lens and it gets refracted, and the image formed will be here. And what about the focal length? If the parallel beam of light falls on the lens, it gets diverged and the rays appear as if they are emerging from a common point. So in the same side of the object, the focal length will be. So this is to give the sign for the distances. H, height of the object. As the object is placed above the principal axis, H is taken as positive +3. Focal length, according to the sign convention, distances are measured from the optic center. So optic center to the focal length, the direction of the measurement is opposite to the direction of the incident ray. So F value is -21. In case of concave lens, focal length is negative. Now object, again you are measuring, here is the object. So object distance 14 centimeter, how to measure from the optic center to the object. Again it is opposite to the direction that of the incident ray. So U is also negative. Okay. Which formula can be used to this? F is given, U is given. So thin lens formula is used, as there is an equation in case of mirror, a mirror equation. There is a thin lens formula, and the formula is -1 upon U plus 1 upon V is equal to 1 upon F. What is required? V value is required. So we retain the V on one side. The remaining quantities will take on the other side of the equation. 1 upon V is equal to 1 upon F plus 1 upon U. Now substitute the values. 1 upon V is equal to, F value is -21. 1 upon -21 plus 1 upon -14. The LCM that you can take is 1 upon V is equal to 42 -2 -3. So you can get 1 upon V is equal to -5/42, or V value is equal to -42/5. So this is equal to -8.4 centimeter, -8.4 centimeter. So the image distance is -8.4. So position is calculated. Remaining is nature of the image and size of the image. So first we'll calculate the size of the image from the relation H dash by H is equal to magnification, image height by object height, which can also be equated to image distance divided by object distance, V by U. So you can equate this as H dash by H is equal to V by U. We require only H dash, so H dash is equal to V by U into H. Substitute the values. V value is -8.4 divided by U is -14 into 3. H dash is equal to 1.8 centimeter. So H dash is 1.8 centimeter. Look at the sign to the H dash. Is it positive or negative? If it is positive means the image is above the principal axis. Compared to the object size, object is of 3 centimeter, image is of 1.8, then you can say image is diminished. As it is having positive sign, it is above the principal axis, image is erect. As the V value is negative, then the image is formed at the same side of the lens where the object is there. So you can say image is virtual. So you can say image is virtual, erect and diminished. The next question is, a convex lens of focal length 0.24 meter of refractive index 1.5 is completely immersed in water of Ri 1.33. Find the change in the focal length of the lens. So first we'll write down the given quantities. Ng, refractive index of the glass, is 1.5. Refractive index of the water is 1.33. The focal length of the lens, Ng, focal length of the glass lens, is 0.24 when it is immersed in water. Let f dash g be the focal length of the glass lens when it is immersed in water. Let R1 and R2 be the radii of curvature of the two lenses. So when the lens is in air, how do you write the equation? Which formula has to be used? The lens maker's formula. So what is the equation? 1 upon f focal length of the material is equal to Ng minus 1. It is actually N21 Nga, glass with respect to air. In the first case we are placing the glass in air. So Nga minus 1. Nga is as good as writing Ng only, because Nga is equal to Ng, refractive index of glass, into 1 upon R1 minus 1 upon R2. Substitute the values. 1 upon 0.24 is equal to 1.5 minus 1. 1 upon R1 minus 1 upon R2. So the equation becomes 1 upon R1 minus 1 upon R2 is equal to 1 divided by 1.5 minus 1 is 0.5. When you cross multiply, 0.24 into 0.5. Let this be equation 1. Now, if the lens is immersed in water, when lens is immersed in water, then the equation becomes 1 upon Fg dash, the focal length of the glass when it is immersed in water. The equation is Ngw, that is refractive index of glass with respect to water, minus 1 into 1 upon R1 minus 1 upon R2. So Ngw you can write as Ng by Nw minus 1 into 1 upon R1 minus 1 upon R2. Substitute the values of Ng and Nw, that is 1.5 phi divided by 1.3 minus 1. So in place of 1 upon R1 minus 1 upon R2, you can substitute this value from the equation 1. That is 1 divided by 0.24 into 0.5 1 upon Fg dash, focal length of glass in placed in water medium. When you substitute, you are going to get 1 upon Fg dash is equal to, this value is 0.1278 divided by 0.24 into 0.5 is equal to 0.9389. Approximately you can equate it as 0.94. How do you write the change in the focal length? Change in the focal length is delta F is Fg dash minus Fg is 0.94 minus 0.24 is equal to 0.7 meter. So this is change in the focal length of the lens when it is placed in a water medium. The next question is, a prism of angle 60 degree produces angle of minimum deviation 40. What is the Ri, and calculate its angle of incidence? So the equation for angle of minimum deviation is n is equal to, n means it is n to 1, refractive index of second medium with respect to first medium. Ng, as the prism is placed in air medium, it is Nga. So as good as writing n only. So refractive index of the material, n is equal to sine of a plus d by 2, the whole thing divided by sine of a by 2. So n is equal to sine of a value is 60 plus 40 divided by 2, the whole thing divided by sine of 60 by 2. So n value is sine of 50 divided by sine of 30. N is equal to 0.766 divided by 0.5, which is equal to 1.532. Refractive index of the material of the glass is 1.532. At minimum deviation, angle of incidence is a plus d by 2, which is nothing but 50 degree. So angle of incidence at minimum deviation is 50 degree. The next question is, at what angle should a ray of light be incident on first face of an equilateral prism so that it just suffers the total internal reflection at the other face? Now we'll see the diagram of that question. So if this is the incident ray at the first face, draw the normal to the surface. This is the angle of incidence. So what should be this angle of incidence I, so that this is the refracted ray inside the prism. So the emergent ray just suffers the total internal reflection, means it should just graze along the surface of the prism, second face of the prism. So this is normal to the surface at the second surface. So if the emergent ray just grazes along the surface, the emergent ray is 90 degree and the R2 is equal to C. R2 is equal to C. So first we'll apply the Snell's law at the second surface. For total internal reflection, E is equal to 90 degree. The Snell's law is N is equal to 1 upon sine C, or C is nothing but R2. Sine of R2 is equal to 1 upon N. Sine of R2 is equal to 1 upon 1.5. So sine R2 1 upon 1.5 is 0.6666. So R2 you can calculate by taking the sine inverse. So sine inverse of 0.66 is R2 value will be 41 degree 48 minute. This is the value of R2. From the equation, the relation between angle of the prism R1 and R2, you can write A is equal to R1 plus R2. R1 is equal to A minus R2, which is equal to 60 minus 41 degree 48 minute, which is equal to 18 degree 12 minutes. So R1, that is the angle of refraction at first surface, is 18 degree 12 minutes. Now you can apply the Snell's law for the first surface, which is nothing but for first surface N1 sin I is equal to N2 sin R. N1 sin I is equal to N2 by sin R. So N1 is the air medium for the first surface, N2 is the glass medium. For air medium, N1 is taken as 1. So the equation becomes sin I is equal to N2 is 1.5 into, this is sin R1, 1.5 into sine of 18 degree 12 minutes. Sin I is equal to, when you multiply 1.5 into sine of 18 degree 12 minutes, you are going to get 0.4677, or I value is sine inverse of 0.4677. So I value is equal to 27 degree 48 minutes. It means the incident ray should be at an angle of 27 degree 48 minutes, so that the emergent ray just grazes along the surface, along the second face of the prism. The next question is, so there is a small bulb which is placed at the bottom of a tank. Suppose if this is the tank, at the bottom of a tank, water tank of depth 1 meter. So a bulb is placed at the bottom. So what is the critical angle for water-air interface? Because this is the surface of the water above which air is there. So what is the critical angle for the water-air interface? And calculate the area of the surface of water through which light from the bulb can emerge out. What happens when the bulb is placed inside a tank? So here is the bulb placed. The light from the bulb emerges out in the normal direction, in the perpendicular direction. If the ray of light comes from the bulb at the surface, it is the interface of water and air. It gets refracts and moves out. Again, if a ray from the bulb comes, it meets the interface of two media, it comes out. So here, if the ray coming from the bulb is incident on the water air interface at an angle of C, then it grazes along the surface of the water. Further, the next ray which is incident at an angle greater than C, it reflects back into the water itself. So the light is not coming out of the tank. Only the light is coming out of the water surface till the angle lesser than the critical angle. So here is the circular area formed by that refracted light. Apart from that, apart from that area, light is getting reflected. There is a total internal reflection of light. So we have to find the area of the water surface through which light is getting emerged. For that, we'll consider the ray of light coming from the bulb which is incident at an angle of C. So this is normal to the surface. This ray is incident at an angle of C, for which the refracted ray grazes along the surface of the water. Now, as the source of light is 1 meter away below the surface, so this will denote as S. This point will take as O, this as B and A. For critical angle, C, if this is a C, from the geometry, from the diagram, we can write this angle as C. So angle of incidence I is equal to C. So for this we can write angle C sin sin C is equal to 1 upon n. Sin C is equal to 1 upon 1.33. Sin of C is equal to 1 upon 1.33 is 0.75. So C is equal to sin inverse of 0.75, which is equal to 48 degree 36 minutes. Now look at this triangle SOB. From a right angle SOB, right angle triangle SOB, tan C. From right angle triangle SOB, you can write the equation for tan C. Tan C is OB divided by OS. From this you can write OB is equal to tan C into OS. OB is equal to tan C. Tan of OS is 1 meter. So tan C is tan of 48 degree 36 minutes into 1 OS value. OB value is 1.1342 meter. So the radius of the circular area through which light is passing is OB, which is nothing but R, having a value of 1.1342. Now we'll calculate the area. Area is equal to pi R square. Pi R square is equal to 3.142 into A is equal to pi r square. So 3.142 into 1.1342 the square. So the final answer area will be 4.04 meter square. The next question is last question. A parallel beam of light is incident on a face of a equilateral prism. What is the Ri of the material of the prism? What is the Ri of the material of the prism if the angle of deviation is 40 degree? So D value they have given 40, angle of the prism A value is equal to 60. So the equation Ng is equal to sine of A plus D by 2 divided by sine of A by 2. Substitute the value, it is sine of 60 plus 40 by 2 divided by sine of 60 by 2. So Ng, refractive index of the glass, is sine of 50 by sine of 30, which is equal to 1.532. So this is refractive index of the material of the prism when it is placed in air medium and angle of minimum deviation is 40 degree. So when the prism is placed in water, let D dash be the new angle of minimum deviation. So now refractive index becomes NGW. That is refractive index of glass with respect to water, because prism is placed in water. So it is sine of A plus D dash divided by 2, the whole thing divided by sine of A by 2. So D dash is the unknown quantity in this equation. So remaining all the things we take it on one side except the D dash. So NGW can be written as NG by NW into sine of A by 2 is equal to sine of A plus D dash by 2. So Ng by Nw is 1.532 divided by 1.33 into sine 30 is equal to sine of A plus D dash by 2. Sine 30 value is 1 by 2. When you simplify this whole left hand side, you are going to get 0.5759 is equal to sine of A plus D dash by 2. So we want D dash, so sine has to be removed. How to remove? By erasing it? No, it have to take it on the other side. So sine becomes sine inverse. So sine inverse of 0.5759 is equal to A plus D dash by 2. Sine inverse of 0.5759 is 35 degree 10 minutes. 35 degree 10 minutes is equal to A plus D dash by 2. So A plus D dash is equal to 2 into 35 degree 10 minutes. It is A plus D dash will be equal to 70 degree 20 minutes. So D dash, angle of minimum deviation, is 70 degree 20 minutes minus A. which is nothing but 60 degree, 70 degree, 20 minutes minus 60 degree. So angle of minimum deviation is equal to 10 degree, 20 minutes. So these are the few questions on ray optics. Apart from this, you can try few more simple examples.